How is the weather in Canada? Can you hear me?
Sorry, Dr. Nagendra, I have trouble hearing you now.
Okay, how is the?
It's good. I will show you some temperature charts later. This is the best season we can get in Canada right now.
Okay, very nice. Okay. Okay, just to give you introduction to the air quality management lecture series. So this is the 45th air quality management lecture series. We started this in 2020 October. So every month we are having one lecture. So basically, this is a first of its kind in India, and the idea is to provide it's a platform for researchers, students, and also the the sharing and also to networking and collaboration. Okay, next. So these are all some of the speakers, past speakers who gave lectures, and you can see that they're all eminent and work air quality management, and translated by Prashant. Next. So, you know, air management lecture series also helped us to start Air Quality Management Association. Adding value to our air quality management lecture series. It provides a platform again for larger networking. Okay, next. So this is another network where this is a grant supported by UKRE, and we started this air quality management, clean environment for planetary health in initiated by the CEPHA network, where the large number of universities across the Asia and the UK started this. Next. Okay, so the other important aspect of our lecture series was also supported by Indian International Conference on Air Quality Management. So this is we started again 8 years back with conference, Indian International Conference on Air Quality Management, which again provides an opportunity for exchange of students from different universities. They will all come and participate, and also knowledge sharing happens with this conference. And we welcome again almost all the colleagues and students to look this opportunity to participate in the air quality management conference. Next. Welcome, Zhao, and thank you very much. We had met about a month back, and very excited to see your research. So I request Chaitra to introduce you, and again welcome all the participants, to this air quality management lecture series. Thank you, Ran, for agreeing to give a talk for this air quality management lecture series. Chaitra, please introduce the speaker.
Yes, sir. It is a great pleasure to introduce Dr. Ranzo. Dr. Ranzo is an assistant professor of chemistry in the University of Alberta since 2018. Soon in July 2024, he is going to be promoted as an associate professor. Dr. Ranzo completed his bachelor's and PhD in environmental chemistry from the University of Toronto, Canada, and his postdoc was from the California Institute of Technology. His research team works on atmospheric chemistry, air quality, and climate change, and his specific research directions include wildfire emissions, indoor air quality, cloud water chemistry, and development of low-cost sensors. Dr. Ranzo has been recently awarded as the 2023 Chemistry Professor of the Year and 2024 University Award for Outstanding Mentorship in Undergraduate Research. It is an immense pleasure to have you as a speaker on our 45th Air Quality Management Lecture Series. We welcome you, sir. Kindly share your screen to start the presentation.
Yeah, thank you very much for the introduction. I would like to share my screen now. Okay, so this is actually my first time using WebEx. So can you confirm that you can see my share screen and then also hear my voice and camera really well?
Yes, Ran, it is very clear.
Okay, thank you very much. And then I shall get started. So thank you very much for me to give me the opportunity to speak to everybody here to make a contribution to the Air Quality Management Lecture Series. It's my great pleasure to be here, and thank you very much for Dr. Shiva Nagendra for your kind invitation. As introduced, my name is Ran. I'll be talking about indoor air quality measurement using low-cost air quality sensors. So before I start my talk, I would like to acknowledge that the University of Alberta is situated on the Treaty 6 territory, which is the traditional homeland and gathering place for the First Nations and Métis people. Great. So, okay, so maybe this is unnecessary for the audience we have here today. I would like to motivate the importance of clean air. So this slide summarizes the data from a 2020 Lancet paper on the global scale risk health factors. Sorry, I'm just trying to get used to the screen here. Okay. And then so the diagram on the left-hand side is for female data, and the one on the right-hand side is for male data for the global risk factors ordered in the rank of their importance. So as highlighted by the green arrow on the left and on the right, air pollution is being ranked in number 4 in both of the sexes, meaning that they are more important than many other important health factors in the world, making people sick by a variety of different symptoms. The color coding here shows that the air quality can induce a number of complications, including cardiovascular, respiratory, circulatory, and also prenatal complications. And altogether, air pollution is contributing to over 6 million premature deaths every year at the global scale. And also, it's important to point out that the air pollutants are around in both outdoor and indoor environments, which leads to our motivation to study indoor air quality. So the pie chart on the left-hand side is an average US person, the places that would spend their day. So long story short, the message here is that other than this 7.6% green piece of pie says outdoor, this person would spend the majority of the day in some kind of indoor environment. And on the right-hand side, as you can see, this is the typical, not typical, stereotypic, I would say, North American single-family style housing. The purpose of showing here is that for us to realize there are a lot of activities indoor that can serve as unique indoor sources of air pollutants, and many of them are not well studied. And ventilation and air exchange is very important in this context because it dictates the period of time that the air pollutant can be sustained in the indoor environment. And finally, the indoor environment is very different. My home is very different from other people's home. And of course, housing in Canada, for example, will be very different from housings in India. So that heterogeneity is a persistent challenges that face indoor air pollutants, indoor air research. So speaking about differences between Canada and India, so here I put one slide for this talk to show where I'm from and then what kind of climate zone I'm located in. So at this moment, University of Alberta is located in the city of Edmonton. So this is my city, you can see right here. This is the map of Canada. So we're very cold, especially in the winter. So I'm here to give you a warning that you'll be seeing a lot of temperature values that are extremely cold. And they are not mistakes, they are real temperatures. So on the bottom, I decided to put out Google information on the average temperature in Chennai and also Edmonton, as you can see here, Right now we're in June, so apparently the average high and low temperature in China is 37 and 27 degrees C. That is the temperature that I don't see in Canada. As you can see, our hottest time is 23 degree and 12 degree in the summer. And conversely, in the winter, you can see the high and low at -7 and -16 degree, and that's an average. So you can see there are certain days that are much, much colder than that temperature. So due to the cold climate in Canada, our buildings are made very airtight. So there's very little gap in the building. What it also means is that the ventilations heavily rely on mechanical ventilation, and natural ventilation is not a very prevalent way to exchange air in Canadian housing and buildings. So that's something I would like you to keep in mind before I proceed further into my talk. Okay, so so how do we measure air quality for both indoor and outdoor? Well, here's a spectrum of instruments and their price ranges that people use to measure air pollutants. The rule of thumb here is that you pay for what you get. So if you can afford and willing to pay the money, in general sense, you can afford. Okay, somebody cannot hear me. Can you confirm that you can hear me right now, Dr. Nagendra? Okay, maybe people really cannot hear me.
Yeah, we can hear you, Ran.
You can hear me? Okay, thanks
Yes,
for
yes.
confirming, because I wasn't sure. Somebody seems to be having trouble hearing me, but it seems like that's not the problem. Okay, so I shall continue. So among the spectrum of air quality measurement, starting from the left-hand side, this is what I'm talking about today. This is the so-called low-cost air quality sensor, or called microsensors. Their accuracy is usually ±30%. It's good for educational and information originally, but I'm applying that for research. So the price range of this is very low. It's about 150 Canadian dollar. I did convert that to Indian rupee, which is about 9,000 Indian rupee, just for your context. And moving up the ladder, there are instruments these days the government in Canada and US started using as supplemental monitoring strategies or human exposure purposes. Depending on which grade of instrument you buy, they can usually settle at around a few $100 to a few $1,000 Canadian. And for regulation and regulatory monitoring, however, we have to rely on research-grade instruments, usually housed in governmental run trailers, to monitor air quality continuously. So each of this instrument is somewhere between 10 to 50,000 Canadian dollars. So now you can make a comparison of the price range. Plus you have to pay for the maintenance fee, so the cost goes up. And finally, for atmospheric chemists like myself and my research group, we always dream about those $1 million instruments that can give you a very robust, accurate, and a high resolution measurement. Those are, for example, here, the proton transfer reaction mass spec. That's usually over $1 million Canadian dollar. And because of that price, it still remains as a dream on my group as well. So that's the range of instrument that we see in air quality measurement. And now the question is, how did indoor air quality research done in the past or traditionally? So traditionally, it's being done by using one or a very few number of research-grade instruments. So I'm pulling this diagram from a paper by Yang et al. They measured air quality in a Chinese student dorm. So what they did is that they put up two research-grade instruments, in this case, ozone monitor, one indoor and one outdoor. That's how they correlate in and outdoor ratio of air pollutants. So the issue here is that these research are often conducted in empty rooms or experimental room for a very short period of time. And that doesn't reflect the real living space. And also, if you look at the diagram here, this is only one room out of many, many rooms in the floor. So the representativeness is very limited. So the switch of strategy from a few research-grade instruments to a larger number of sensor of instruments really began in the past few years. The diagram on the right-hand side is from this paper by Delphine Farmer at Colorado State University. She wrote an overview paper for this campaign called HomeCam, which is a big indoor campaign, happened a few years ago. As you can see, the strategy here was to apply multiple sensors in every corner of the household for actual activities in there. So this effort has just begun. I think this is where people are making a transition, looking at low-cost air quality sensors, because in my opinion, low-cost sensor really enables new research approaches in many aspects. Because of their low cost, you can deploy many different sensors simultaneously in multiple units, for example, in a multi-dual buildings like this one. Or you can even deploy in different places inside a house, like the diagram I showed in the previous slide. you can get personalized indoor air quality. So for example, I can know about my indoor air quality without relying on the governmental stations that are kilometers away from my own home. And everything can happen in real time as well. So you can see things happen in front of you. Any action you're taking in indoor can be reflected right away by the air quality parameters in there. The accessibility of low-cost sensor can also enable community-based research. This is why in the conference that I met Dr. Nagendra a month ago in California, there was a huge component about community-based research in this low-cost sensor conference. And a lot of us, therefore, believe that low-cost sensor is the breakthrough to overcome some of the environmental inequity that's currently existing in the context of air quality monitoring, because governmental-run monitoring stations are inevitably in concentrated populated city centers, leaving a lot of remote communities such as indigenous community in Canada not covered in the range of measurement, making them underrepresented in the context of air quality monitoring. And low-cost sensor has the potential to overcome that. So now let me talk a little bit about the sensor that we use for our study. So the sensor looks like a little lunchbox. We call it a wooden box in here, is the size of my face. And then it's the joint effort of a number of undergraduate students and research associates in my group over the past years, including Ryan Duruso-Kunz, Ariel Dirormi, Wayne Chung, and Sohaib Omar. So if you open the box, you will see several components in the sensor. The central piece here is a microcontroller that will communicate with sensor pieces. So here we buy the sensor pieces from online platforms such as Amazon or Alibaba Express, those things you may or may not know. So so on one end, we have the CSD30 sensor to measure CO2, carbon dioxide, temperature, and relative humidity. On the other hand, we use the NOVA SDS011 to measure PM2.5 and PM10. The microcontroller has Internet of Things technology, so we can send the data in real time onto an online platform called ThinkSpeak, such that the researchers and the participant will be able to see the data in real time. So the reason we chose these parameters in our sensor, obviously because their importance in the indoor environment. PM2.5 or particulate matter smaller than 2.5 micrometer they're very important pollutants both outdoors and indoors. They're used as benchmark air pollutants in many different countries in the world. And carbon dioxide, on the other hand, is exhaled in our breath at a concentration about 5%. So CO2 in the indoor context is used as a tracer for ventilation and also the crowdedness in the indoor environment. And finally, temperature and relative humidity are used as conditions for thermal comfort indoors. So using this sensor, my research group has applied that to multiple purposes and projects. In this talk today, I'm going to briefly introduce 3 studies. The first one is about indoor air quality in student residences. And the second one is about how wildfire smoke from outdoors can infiltrate into campus buildings and affect our indoor air quality. And finally, in study 3, I'm going to switch the gear a little bit and then talk about a very different study where we're trying to look at the air quality in a commercial chicken farm. Okay, but before I jump into the details of the study, let me start from the accuracy, quality control of the sensor. So when I tell you that the sensor is only 150 Canadian dollar or about 9,000 Indian rupee, the first question, of course, is, are they reliable? Do they provide accurate data or reading? Accuracy, indeed, is the challenge that continue to face low-cost sensor research. So from the experience and other people that we learned from in the past few years, co-location and cross-calibration against the research-grade instrument is very important in ensuring the quality of the data. So for example, in the picture, here is a Roshan, you'll see her picture over and over again. We put our sensor into an empty office and we co-located with a research-grade instrument. This little box here is a green particle, optical particle sensor or OPC that's 20,000 Canadian dollars. So it's a legitimate research-grade instrument. And then we calibrate them together to make sure that our reading is in agreement. And also some details here is that we try to use the real particles for this cross calibration. What does it mean is that for indoor measurement, for example, this one here, we use a humidifier as one kind of representative indoor particles, so we can look at the response to real indoor particles. And for wildfire smoke, we let the wildfire smoke come from outdoor and use that for cross calibration. And finally, for chicken particle, we brought everything into the chicken farm. We use the real particle suspended in the chicken farm for intercomparison. So using that real particle is a very important part in ensuring quality of the data. And the diagram on the right-hand side is example data, a time series of PM2.5 over time for the inter-comparison study. The blue lines here, many of them are all the microsensor, the low-cost sensor that we studied, put it in the room. And the yellow shaded area is a reading by the optical particle counter, the research grade reference instrument. So as you can see, the agreement is pretty reasonable up to 100 microgram per cubic meter, but there is some deviation above that. So what we did is that we had to apply a sensor-specific calibration or correction factor to ensure that the accuracy of the sensor is in the reasonable sense in here. Okay. Okay, so with that in mind, I'm going to move on to the first study that I'm going to present today. It's the indoor air quality in university residences. The study was led by Roshan Afroz, a PhD candidate from Bangladesh, and then Xinyang Guo, a PhD candidate from China. The paper was published last year in Royal Society of Chemistry's Environment Science Atmosphere. Okay, so the motivation of the study is that 22% of US university students apparently live on campus residences, so live on campus. And last year, when I visited India, I found that the situation can be quite different in IIT campuses. So the residency rate on IIT campus apparently can be much higher. The picture I took here last year at IIT Kanpur, I stayed there for 2 weeks. I found that the majority of the student and the faculty member were actually all living on campus. So that's just how important the air quality in the indoor environment in student residency can be so important for the health and well-being of students. That being said, there are very few studies out there that actually focused on indoor quality in student residences, and particularly there's none in Canada. I was surprised to see that. So looping back to the figure that I showed you before, and the previous study was all performed on unoccupied testing units, and then over a short period of time, and also the variability and heterogeneity in indoor air quality was not reflected. So with that gap in mind, our objective is the case study using a network of low-cost sensor to assist the university's resident surface to identify indoor air quality issues and ventilation challenges in here. And from our point of view, we wanted to perform a continuous monitoring in an actually occupied. So we want to sign up to an actually messy area to see how the student life is affecting the indoor air quality. And of course, engaging with the student community is also part of our motivation behind this. Okay, so we chose 5 different residences on the campus, and then and we approached it pretty strategically. So we chose the building by like high rise versus low rise, and whether cookings are allowed or not allowed. Is there any other source of potential air pollution inside the building or not? And also ventilation scheme, just to point out that the building E here, so all the other building has this mechanical ventilation called HVAC system. So, heating and an air conditioning system in there. But the building E here is a little bit older building. It doesn't have the duct to circulate the air, but instead the heating is relying on so-called peripheral heating. So the hot water pipe, for example, on the wall to heat the building. So the ventilation scheme is quite different. So we deployed a total of 35 sensors across these buildings, and then we monitored from November 2021 to April 2022. That is the coldest period of winter in Canada, and that's also when the semesters are going on, so the residents are filled by students. Okay, so starting from some overall indoor air quality trends in here, on the diagram on the left-hand side, I'm showing you the campaign overall averaged CO2 concentration in 5 of the building A to E that we measured during our campaign. So what you see here is that for 4 of the building A to D, the median of the CO2 concentration is about 600 to maybe a little above 700 ppm. So given that outdoor background CO2 is 420, 600 to 700 ppm indoors in Canadian buildings is pretty typical, again, due to the air tightness, right? But what we saw is that building E here in purple had a particularly high CO2 concentration at 900 ppm. That's a little bit high even for a Canadian indoor environment. So we decided to investigate further on what could be the potential reason for that. So what we did is we used the data to derive the air exchange rate. So as you may know, every time when there's an event going on in the indoor, there's a spike in the CO2 or particular concentration, there will follow a first order decay, and the first order decay rate will be corresponding to the air exchange rate. So from the data, we were able to calculate that first order air exchange rate in the unit of per hour. So the diagram on the right-hand side is this first order air exchange rate in building B and C versus E. So as expected, building E had half the exchange rate from the other building. Because again, if I go back one slide, on this slide, I showed you that this is building E. That's the one doesn't have the HVAC system, but instead has the peripheral heating. So we don't have airflow in the building. So not surprisingly, that likely led to a much slower air exchange rate, and that in turn led to a much higher indoor CO2 concentration. So that's something we found from this study. And then we moved on to identify the major source of indoor PM 2.5 from in student residences. And long story short, we identified two different sources. The first one is the use of ultrasonic humidifier, and the other one is cooking. So if you know, Canadian winter can be very cold, so the indoor air gets very dry because when we heat up the outdoor air into a higher temperature, the relative humidity will drop significantly. So prompted by dry air, many students will choose to buy their own humidifier and make their air a little more humid so they feel a little more thermal comfort in there. And then also, if you didn't know, ultrasonic humidifier can be a big source of PM 2.5, and my own group has studied about that before. So ultrasonic humidifier has this thing called piezoelectric transducer inside that's going to oscillate at an ultrasonic frequency. That frequency crashes water into small water droplets. That's going to be the mist coming out of the humidifier. But when the mist evaporates, there will be a lot of particles that's left behind as PM 2.5. So the diagram on the left-hand side is a unit or participant indicated that they used humidifier during this winter. So I'm showing you the PM 2.5 on the left-hand side, and then indoor relative humidity on the right-hand side over a period of maybe 1 or 2 weeks in January 2022. What you can see here is that for the period that the student indicated the use of humidifier, you can see there's a jump in both the PM concentration and the relative humidity. Our sensor was perfectly suited for this purpose because the sensor recorded PM and RH at the same time. And the concentration of PM 2.5 is also not very low. You can see easily over 100 microgram per cubic meter. As you know, as specialists in air quality management, this is the concentration usually representative for like a polluted city or something. So humidifier is making a lot of particles in that regard. And diagram on the right-hand side is another unit where the participant indicate that they cooked regularly. So the concentration of PM 2.5 is on the right axis, showing by this green shaded area. You can see the really nice sporadic jump in PM 2.5 corresponding to the period where the participant cooked their meals. And we also identified some impact from outdoor air, of course, even though the Canadian buildings are quite airtight, but there is air exchange in and out. So what we see here is that on the top panel, we're looking at PM 2.5 concentration over about 2 weeks period in March 2022. The top panel is outdoor air, so it's measured by a purple air sensor nearby the campus. We see this trend of PM 2.5. And what we saw indoor from resident B and A is that there's very good correlation with outdoor PM concentration. I'll bet there seems to be a little bit delay in the time trend, meaning that the air took some time to get into the building. So that's something really interesting. And this trend was particularly significant for building that prohibited cooking. So there's no other indoor source, and outdoor source becomes very important. And finally, perhaps unique to Canada is that the meteorology really matters, especially in the cold winter. So here we're looking at the period from December into end of January or February 2022. The top panel is outdoor temperature, okay? And you can see a value of 30, and then it said minus 30 in here. I warned you guys earlier that it's not a mistake, it's real temperature. Yeah, we do get minus 30 degrees C once in a while, and that's one of those periods in here. So what we saw is that when the outdoor temperature is extremely cold at minus 30 degree, in some of the residences, we saw a jump, accumulation of CO2 in this case, or particular matter in some residences as well. So after communicating with the resident services on campus, we found that when the temperature is too cold outside, the buildings are forced to reduce the ventilation rate to keep the thermostat going. And also there's a chance that the fan on the top of the building is frozen over, so the ventilation kind of stops. So that likely led to the accumulation of CO2 and particular matter. And then also along with this, other indoor air pollutants were likely accumulated. So there is challenge related to ventilation in extremely cold weather. Okay, so a quick summary for my study one. So indoor air quality in student residences. This was the first study of indoor air quality in student residences in Canada. We think that the low-cost sensor provided tremendous insight into IAQ situation that was not achievable using traditional instrument from research. So we found that for indoor source, humidifier and cooking were the most important. And ventilation rate and scheme is very important, and also meteorology can significantly affect that. And finally, outdoor air pollution can certainly be a source for indoor air quality. In the winter, the air is relatively clean, but in the summer in Canada, we have this thing called wildfire smoke, which naturally transitioned into our next research question. What about wildfire smoke in the summer? How do they affect our indoor air quality? So I'm going to make this transition to the second study I'm going to show you today. So wildfire smoke infiltration in campus buildings. Again, this was led by Rochon Afros with the help of 2 undergraduate students, Sohaib Omar and Jared Alonso. So here's a picture of Edmonton, a beautiful river valley, except that it's been ruined completely by this thick smoke from wildfire in the summer a couple of years ago. So if you didn't know, Canada is facing a huge challenge in terms of environmental issue with wildfire. So 2023, if you read in the news, is the worst fire year in Canada. In fact, in the single year, we had 18.5 million or 1.8 crore hectare of land burned in that single year. I try to put that into context that's more relevant to people at IIT Madras. So I looked into the total area of Chennai, and then the total area of Tamil Nadu, which is apparently 13 million hectares. So what does it mean is that in a single year in Canada, an area that's larger than Tamil Nadu actually burned off. That's just how much land was burned last year. And the diagram on the left bottom corner is the monthly average PM 2.5. We took the data from local governmental authority. You can see that in 2023, which is the purple bar on the right-hand side, we had by far the highest PM concentration in the summer months that's hit by the wildfire smoke. And the bad news here is that the acceleration of the frequency and severity of wildfires is actually by the climate change. So this is not going to be the problem that will soon go away, unfortunately. So the motivation here is that the government of Canada is trying to encourage people to stay indoors and protect the indoor air quality. But their guidance is very vague. And it's not specific for certain indoor environment. And more importantly, if you don't have a means of measuring indoor air quality, how do you know when and how to take that action there? So with that in mind, our objective is to investigate how wildfire smoke can affect indoor air quality, and particularly So sorry, I'm getting a pop-up in here. I don't know what was that. So in particular, we've tried to determine this indoor and outdoor ratio of PM 2.5, which is very simple, literally the concentration of indoor PM over the same time outdoor. So if this ratio approach 1, that means the indoor is not providing any help to filter out particles. And then inversely, if this ratio is approaching 0, that means the building is doing a very good job filtering out the particles. So we try to build an understanding about this in and out ratio, and the university campus is actually an ideal place to do that because there are different kind of buildings, including offices, labs, libraries, residence, hospitals, etc., etc. So we also try to build a platform to inform the danger of the wildfire smoke to our campus community. I'll start from that part. So my team, led by Jared Alonso, the student I showed you earlier, we built a website so you can see, and then our sensor can communicate with the internet. So we can crop data in real time. So our community member can go to the map, click on any of this building or sensor, and jump into another page, which is showing the real-time indoor air quality. So we deployed 28 sensors on the campus, and this website was open for our campus community to really understand the real-time indoor air quality. So now let me show you some data. So here I'm showing PM 2.5 concentration as a function of time over the entire summer last year. So here I'm comparing the outdoor governmental station data, which is in green, and versus the indoor air quality data measured by all of our sensors averaged together. So first of all, we had a pretty dirty summer. You can see once in a while, the outdoor concentration is over hundreds of micrograms per cubic meter. So we certainly had some really bad wildfire smoke events over the past summer. And the indoor concentration on average shows a very good correlation with outdoor, and it's much lower. So that means indoor air quality is significantly affected by outdoor air, but it's protecting us by filtering some fraction in there, which is good. And then we decided to look further into this in and out ratio, and we found that there seems to be a difference between buildings equipped with different grade of filters. So the filters had this rating called MERV, or minimum efficiency reporting values. So on the right-hand side, you can see here that MERV 8 and 13, the greater the value in the rating, the more efficient it is to filter out the small particles. So you can see MERV 13 is much more efficient in filtering out small particles down to 1 micromolar or smaller. So now on the diagram, I'm showing the in and out ratio of PM2.5 over the same summer period. So what we see here is that compared to buildings equipped with MERV 8, the lower grade of filter, the buildings equipped with MERV 13 seems to have a much lower in and out ratio, meaning that the higher grade of filters is more efficient in protecting residents from the infiltration of outdoor particles. And we also looked at the ventilation rate of the building. So the university actually published the measured ventilation rate on the website. So we were able to kind of correlate each building's ventilation rate. So here's a diagram. So again, this is in and out ratio of PM2.5, and we're plotting that for each sensor or building in a box plot. So we're ranking them in the order of their ventilation rate rating. So what we found is that when the ventilation rate of the building exceeds over 10 per hour, so that's the first order decay rate I mentioned earlier, it seems like the in and out ratio is jumping up. So it's more outdoor particle going into indoor. So this is a little bit confusing because indoor, usually ventilation rate is good for indoor air because it filters out, it circulates the air. Especially from the COVID-19 time, we learned that the higher ventilation rate can protect us from potential transmission of virus. So usually the ventilation rate is great. However, during the summer, during the wildfire smoke events, the issue is that the high ventilation rate can inversely hurt indoor air by ventilating more outdoor air into that, represented by a higher in and out ratio, and that's translated into a much higher concentration of indoor PM2.5. That's something we found. So to summarize my study too, we found that the wildfire can penetrate into the building. While the building can provide protection against the outside smoke, the effectiveness varied. In particular, the higher grade of filter is necessary to better filter out those particles coming indoors. And also faster building ventilation, which is usually a good thing, can be unfortunately hurting the indoor environment during severe wildfire smoke events in Canadian buildings. Cool. So I still have maybe a little bit of time left. So I'm going to go through this study 3, which is the characterization of indoor air quality in a commercial air farm. So you can see I'm making a transition from more like a campus residential building into a commercial or industry context in here. Okay. So I'll start by some Canadian context in here. So the Canadian chicken or poultry industry is pretty big. Long story short, the poultry industry itself is supplying 7% of domestic gross production to Canada of all the farming operations. So it's quite big a sector in the agriculture sector in Canada. So if you think about the poultry supply chain, it's pretty massive, and there are more multiple components there. There are egg industry, there are meat industry, and also there are hatching industry to provide the egg that becomes the chicken to lay egg and kind of thing. There are multiple components in the poultry industry. So we've been working with quite a few of them. So the industry is aware that there's a huge challenges related to indoor air quality. So again, the weather is so cold in Canada. So the commercial farms are all indoors. So what you're looking at is this kind of huge warehouse, very big. And then there are thousands and thousands of chickens concentrated in these big buildings, leading to an accumulation of indoor air pollutants, including particulate matter or dust, ammonia, volatile organic compounds, carbon dioxide, etc., etc. So like I said earlier, the industry is well aware of the situation because the indoor air quality is associated with animal welfare, occupational health, and then ventilation rate, which is directly related to energy efficiency, industry profit, and also environmental footprint. And altogether is all related to sustainable farming and sustainable food production into the future. And further to this, so here is particulate matter in chicken farm. And so This is a diagram of a particle deposition diagram. I'm sure you've seen the human version of that, but I'm not quite sure how many of them have looked at the bird version of that, which is very interesting. In human, we know that the smaller particles can penetrate deep into our body. And for the bird situation, a surprisingly similar narration can be seen here. So although the structure in the respiratory tract of a bird is very different from a human, that part is not relatable, but the narration is the same. The smaller particles are able to penetrate deeper into the bird, presumably hurting their health more than the larger particles. So there are very limited information about particles or concentration of particle in poultry farm. So the diagram on the right-hand side, I'm showing you data I took from a master's thesis from Dr. Van Hyes group at Guelph University in Canada. So it's one of the not many Canadian farms. So they used a study that they used the optical particle counter and measured PM2.5 on the top and PM10 on the bottom. So you can see it's day-to-day variation in here. So while it looks familiar as a diurnal trend for particle, what you shouldn't be overlooking is the concentration unit in here. So for PM2.5 and PM10, we're looking at milligram per cubic meter. And as air quality management specialists, you know that in outdoor or indoor, we're using microgram per cubic meter. So yes, the concentration of particles in the chicken farm is typically 1,000 times higher than outdoor, which is pretty crazy. So with that, even with that crazy concentration, there is further potential issue with the transition that the poultry industry is trying to make in the future. So driven by animal welfare and also consumer needs, the industry is shifting away from the caged style of farming. So if you imagine some picture of chicken farm, you may think about two types. One, the chickens are all housed in the cage. They cannot move very much. It's kind of poor and then sad. And the other one is free run, where the chicken can freely run around on the floor. The issue is that the particle concentration is correlated with chicken activity. When you switch from this cage, which is now very good for the chicken health and the welfare, to the free run system, you expect that the concentration of the particle, unfortunately, will go up. So the Canadian egg farmers are committed to make this complete transition by 2036. So in 12 hours, this transition will be complete. But the producers are not ready for that because they don't have an accessible tool for monitoring this elevated concentration of particulate matter in their farms. So this is where my team put our eye onto the low-cost air quality sensor to see if we can make one that works for chicken farm, basically. So the objective here is to offer a better tool to better understand IAQ in commercial poultry facilities. We're trying to test out a low-cost sensor that works in the poultry facility and to monitor air quality using that low-cost sensor. That's our goals in here. And study was again led by Rochon and Xinyang, similar faces that you have seen before already. Okay, so for sampling location, so there's some crazy pictures going on here. I hope you look into this very carefully. So we did our deployment first at an experimental farm in University of Alberta, so we can test our sensor there. And then we moved into a commercial table egg farm, which is housed to 8,000 free-run chickens. So this is a picture in there. This is what it looks like, a huge warehouse, 8,000 chickens in there. So each of this is a chicken. There's a red light because apparently red lights can calm the chicken down, making them less anxious and also produce less particles kind of thing. So it's very smelly and dusty. So we have to wear proper personal protection equipment such as the gas mask and stuff. This is my student working very hard in the dusty and dirty environment in the chicken farm. And this is me just messing around, taking a selfie and stuff, just having fun in there. No, I've been helping my student. That's just kidding. So so when you think about putting a low-cost sensor in an extremely dusty chicken farm environment, you can imagine a lot of things will go wrong. And that is right. We did see a lot of things go wrong. So the picture and data shows everything here. There's so much dust, so our inlet got clogged very quickly, and then the fan was buried under dust and stopped working. And finally, the data you can see, this is PM10 over a period of 2 weeks. First of all, the concentration is too high, and then the sensor stops reading. So we got a sensor cutoff in there. It doesn't really help. And also a week or two later, the sensor data start decaying away. That is not because the air is getting cleaner, but because the sensor stopped working, because clock caging kind of thing. But my team managed to keep trying on different prototype, and at the end we came with way that with a slower fan and also the program fan, so it turns on only when data acquisition happens. we were able to prolong the longevity of the sensor quite well. So you can see by the end of this optimization, we were able to record PM 2.5 and PM 10 over a month or so without any interruption in between, which is pretty good. And we had to recalibrate our sensor using the dust suspended in the farm. After calibration, we were able to bring the agreement between our sensor, which color is that? Our sensor in green, so green is our local sensor, and then blue, the brown is the green OPC into a pretty good agreement. You can see they're reading similar thing in the farm, which is pretty good. And then we tested the performance of our sensor in the experimental farm. The left-hand side is PM10, time series PM 2.5 similar as well. You can see 3 low-cost sensor exhibit a very good agreement with the OPC over this 1 day of test co-location test. We were happy to see the spike of concentration were very nicely recorded by both research-grade reference instrument and low-cost sensor as well. The diagram on the right-hand side is the one-to-one plot. So we're plotting our low-cost sensor against the OPC. You can see, generally speaking, we're gathered around one-to-one line with a pretty linear response. So that's a reasonable accuracy, I would say. And then we moved on to the commercial farm. This is the map of the commercial farm. You can see this is the barn that had 8,000 chicken, and there's another barn with another 8,000 chicken that we didn't go in. So we deployed 5 different sensors in this chicken farm, and we also use our research grade aerodynamic particle sizer and the optical particle sizer to look at size distribution. You can see the majority of the particle is pretty large at around 3 to 5 micrometers. So we're looking at pretty large dust particles. So here's some overall trend that's recorded by our low-cost sensor. You can see the 5 sensors consistently recorded a diurnal trend. This is diurnal trend of PM as a function of the time of the day. So in the morning around 6 o'clock, there's a jump in the particle reaching the peak during the noon. And when chicken goes to sleep, the particle concentration drops. So we're very happy to see that diurnal trend being recorded. And on the right-hand side, we're also showing that there's a huge concentration difference between the nighttime and daytime recorded by low-cost sensor. So the chicken activity is being recorded really nicely. And further, because our sensor, I didn't really emphasize, but we had the CO2 sensor in there, we were also able to track the CO2 concentration in the farm. So there are a lot of things going on in this diagram. Let me quickly break it down for you. So the CO2 concentration is shown in the lighter gray tracer up and down over a period of 2 weeks or 3 weeks in here. You can see the concentration on the left axis. So the CO2 concentration in the farm is over 4,000 ppm sometimes. It's pretty high because you have 8,000 chicken breathing in there. And what we also saw is that there is a general anti-correlation with outdoor temperature, which is shown by the darker black line on the right axis. Again, you see like minus 30 degree kind of thing. It's not a mistake, it's Canada, so it's a real temperature outdoor. So day to day, there's diurnal trend, but if you look at this span of 3 weeks or so, you can see there's a general anti-correlation between indoor CO2 and outdoor temperature. That is because when the temperature is cold, the ventilation rate in the farm is automatically adjusted low to maintain the temperature. Whereas when the temperature gets a little bit milder, the ventilation rate goes higher. The ventilation rate is the red line in here, which lead to a lower concentration of CO2. So we were able to see this correlation between outdoor temperature and ventilation rate, therefore the CO2 concentration in the farm. So let me summarize the third study in here. So to make the long story short, we developed this prototype that seems to work okay in the poultry facilities. And the accuracy is reasonable compared to a reference grade optical particle sensor, which is good. And also, I want to emphasize that, as I mentioned earlier, the producers currently do not have a means of monitoring their own indoor air quality, even though they're forced to make the transition into a more like a free-run, cage-free kind of environment for the chicken, which will face even higher concentration of particle concentration. So this sensor, which makes a 0 to 1 breakthrough, I think it's a significant step towards more automated and accessible environmental monitoring for poultry farms. Okay, so the overall remarks on my study is I hope that I demonstrated to you that the low cost or micro sensors opens new avenues for research approaches because they provide unprecedented coverage of data in space and time, so we can locate the data into places and frequency that has never been done before. The accessibility also enables engagement of the community, do some participatory research in various scales. And also basically overall, I think low cost sensor is a great tool to offer data to those who are actually in need of the data. So with that, I would like to thank you for your attention. First of all, I would like to thank all the current members of my research group shown the picture in here. And again, putting up the picture of all the students who made a contribution to the science that I presented to you today, and all the funding agency that supplied the funds to make the exciting science possible in my research group. And I'd like to thank you again for your attention, and thank you for Dr. Shiva Nagendra for his kind invitation for me to contribute to the air quality management lecture series. Thank you, and I'd be very happy to take any questions.
Yeah, Ren, thank you very much. It's really interesting, exciting research which your group is carrying out. And
Thank you.
we were just like to understand a couple of things like, in the indoor environment where the climate, as you rightly said, the humidity is play a vital role. Did you look at it at the temperature aspect where, how the temperature, humidity, and the particularly PM 2.5 will influencing? For example, in the night time, did you notice there is an increase in PM 2.5 concentration, or is there any possibility for particulates to grow because of increase in concentration? So could you just throw some light on that?
Yes, thank you for that question, Dr. Nagendra. That's an excellent question. So, so indeed, I'll start from general understanding. Indeed, so when the relative humidity is high, generally speaking, the particle can grow larger. And then from the low-cost sensor study that we learned from the conference, there seems to be an overestimate of the sensor against those larger particles. So there is a humidity effect in the general sense. But as I may have shown you earlier, I can pull up some study in here. Sorry, my computer. Sorry, my screen dims sometimes 26. So where should I look for? So if you look at the humidity in the Canadian residents, perhaps here is a good example. So we're looking at the indoor relative humidity of 15 to down to 10% or less in Canada. So this is Canadian winter. So for the period that we monitored, the relative humidity, even at nighttime, was never very high. And in my understanding from my visit to northern India last year, the humidity can be much higher. So the narration can be quite different in other regions of the world, such as India. But in Canada, we looked at the humidity, but we never thought that we would worry about humidity causing any increase in the particle reading or growth of the particles.
Why you have not measured temperature? Is there any reason for that, or do you think that temperature remains constant between day and night time in the indoor environment?
Right. I don't have the temperature data here, but we do have temperature, and it's just simply I didn't put up on the slide here. And then there is temperature variation between day and night. However, during the winter, the air in Canadian resident in this specific example, the student residence, it's very temperature controlled by the central thermostat. So what do you do over the day? I think you're right. It's relatively consistent in the sense that you'll see this circle of heating and cooling down, sitting cooling down. So the thermostat was set to a certain value, and the ventilation or the heating system will just kick in when it's lower than. So we actually don't see the diurnal trend of temperature variation in the indoor environment.
Dr. Shiva, may I ask a question?
Yes, please go ahead.
Thank you, Dr. Zhao, for an excellent and triggering presentation. It was very nice. And we came to know many new things from this presentation. But two questions have come to my mind. One is that you yourself has mentioned in the earlier part of your presentation that the reliability of low-cost sensors is questionable. And it is still under question whether they will give correct data or not correct data. And we still do not have a very reliable method of calibrating these sensors. So how do we rely on these values, whether these values are correct, wherever we are measuring them, whether in the ambient air or in the indoor air environment? That is one question which comes to my mind, how to establish the reliability of these low-cost sensors. Secondly, whatever applications, wherever in the indoor we are using these, we all know that ventilation and sunlight definitely helps to improve the indoor air quality. But in some of your presentation, you mentioned that ventilation in fact increases the indoor air quality. And this may be true in the temperate kind of climates, but in the tropical climates, when the outdoor air becomes very, very less concentrated with pollutants, if it comes into the indoor air also, it helps to improve the air quality indoor. So instead of concentrating on monitoring indoor air, why not we work on redesigning the indoor spaces with the help of architects, builders, and planners? Because they should redesign these buildings in such a manner that the indoor air quality does not become a problem. So these are two of my observations. So would you like to comment on them, or what is your opinion?
Yeah, thank you for those two questions, Dr. Gupta. I'll address your question in order. So the first question was about the reliability of the sensor. What are the strategies to ensure the air quality, the reliability of the sensor, particularly indoor and outdoor? That's an excellent question. And I'm going to go back to, if I can, to that slide, probably. Probably here. Yeah, so you're completely correct that even though we try to do our best to calibrate our sensor, the reliability is questionable. I think questionable is the right term to describe this. After all, because in the sensor, we're relying on very simple scattering module on the laser and a photo detector in there, photodiode detector. There is a lot of study going on. So this is where me and Dr. Nagendra met in the conference. So there's a community of low-cost sensor researchers trying to come up with a better way to calibrate the sensor. For example, some people presented about co-locating a mobile van of research instrument across the city, so you can rotate the proximity of sensors to a research-grade instrument. Hence, you can do a calibration. Some people use a multivariable correlation to do correction based on temperature and relative humidity. And certain people conducted other machine learning approach to really correct the data from nearby governmental run monitoring station. So I think there are a lot of efforts that's going on there, suggesting very creative and potentially feasible strategy to correct the data accuracy in here. Those are something me also as one participant in this community, keeping my eyes open to see what's coming next. And in terms of indoor air research going on, there's no standard way to correct that. And I still believe that the data that we provide, although may not be 100% accurate, because the size, the concentration, relative humidity, as Dr. Nagendra also said earlier, all matters for accuracy. So we're not saying that our data is simply accurate after one calibration. But I think the important thing here is that we're providing data to people that so far never had any access to indoor air quality or measure at places we never measured before. So I see value into there, and this is just the beginning to shed light into there. But of course, there will be future effort goes into ensuring the data quality at a more advanced level. So now I'm going to the second part of the question, which is how about we change the design of the building to use the natural building design to enhance the air quality? I think that's an excellent idea. In fact, I'm going to be honest, I never thought about that because I'm not a building design kind of person. But I think you're right that there can be various things that the building can do depending on which climate zone and what kind of outdoor environment you expect to kind of cooperate into the design to minimize air pollution infiltration to indoor and kind of thing. Again, I don't have insights into there, but I hope that as an air quality researcher, our data from indoor can provide some guidance for those people who are working for this building design to make more informed decision on how to design to improve the air quality. Thank you for that suggestion. I just don't have good answer for that.
Thank you very much. Thank you very much.
Yeah, Ran, there is some couple of questions in the chat box. Can you see whether you can able to read that?
Sure. Let me try to open that. I'm trying to learn how to do WebEx. Okay. Also, my screen doesn't. Oh, here we go. Chat. Okay. Great. I can see this. Okay. Good morning. Please type your question in chat. Okay. So sure, I'm going to address question by Suruthi. Good presentation. Thank you very much. Residential wood burning is a common issue, especially in countries with low temperatures. Have you looked into the air pollution due to residential wood burning? Integrating the study 1, where you have access to IAQ in residential building, and study 2, where you have access to air pollution due to forest fires. That is an excellent question. It's pinpoint on my research because although I did not do low-cost air quality sensor on wood burning, I do have a series of research projects on residential solid fuel burning. So I mentioned earlier that I went to IIT Kanpur last year. I had a really exciting collaboration with Dr. Tarun Gupta there. Our collaboration is actually on the chemical characterization and brown carbon characterization of residential solid fuel. I was more focused on cow dung kind of solid fuel that's not being studied very well. So yes, I believe you're right that the indoor residential burning will supply a lot of concentration of indoor pollutants, and then combining both, my project 1 and 2, it will be an exciting project to study further on that. In fact, I have further collaboration with Dr. Gupta, Tarun Gupta on this regard. But one thing, I don't know if I'm answering your question, but one thing we have to be careful is that these low-cost sensors are not very good at picking up ultra-fine particulate matter. So we actually did one experiment. I do wildfire study. So we have a fire lab, we burn fire, we put a sensor right next to it. And surprisingly, we saw very little particle. That is because depending on how you burn stuff, a big fraction of the particle can be ultra-fine particles, smaller than 1 micrometer or something, or even less. So those particles are not very well scattering light, therefore not very well detected by low-cost sensor. So in addition to the excitement, I think that we should be cautious about how the limitation about this low-cost sensor, its ability to detect those fine particulate matter that's coming out of this residential burning. Okay, so hope that answered that question. I have another question from Dr. Nagendra. In case of wildfires, if ventilation cannot improve IAQ, what would you recommend as a solution to prevent exposure to extremely high pollutant concentration? Will air purifier help when concentrations are so high? That's again another excellent question. I think you're exactly right, Dr. Nagendra. So very timely, actually, I published the article to my university's communication letters to really warn our community members about the danger of wildfire smoke. So in that article, my student, again, Roshan, right on the screen here with me, we said that the building is protecting us from wildfire, but filtering on average only 80%. There's 20% left in there. That's up to you to protect on yourself. So from a building management point of view, what we recommend is that, first of all, use higher grade of filters if you haven't done so. Number 2, because we started seeing the evidence that ventilation rate, which would be usually good, but can ventilate more air, maybe there can be some emergency response procedure in place. When the government say, hey, look out, outdoor air pollution is severe, there's a huge jump in the air quality health index. Then we just kick off this emergency plan to reduce the ventilation rate to shut out those smoke from outdoor. That's one strategy. And from the personal level, what we recommend is use air purifier. Yes, you're right, Dr. Nagendra. And then also we tested this box fan DIY cheap air purifier. It worked in that regard. And also the other thing is simply mask, which we're all used to during the COVID-19. We can use a face mask to reduce the exposure to wildfire smoke. That's my opinion. Yeah.
Yeah, Ren, I just wanted to one follow-up questions on that.
Sure.
The chickens or cocks, they're generally when they, different activities. For example, they have a feathers, so like a lot of dust can deposited on that, and when they are flying or moving, or maybe when they flash their wings, they can be significant increase in dust particle concentration. Have you noticed something like that? Maybe in the early morning hours, or I don't know that the kind of activity the birds will going to have. So if did you get some significant concentration and try to say whether during that period if the ventilations can be increased, can have an influence on controlling the pollution?
Yes, that's an excellent suggestion. And then we did not do a very careful observation about the correlation between specific activities of a chicken with the air quality. But you're correct that in my understanding, certain activities contribute more to particles than other. I don't think this was relevant to our farm, but there are other so-called enhanced furniture farm. They have a sand bath. Chicken like to go to the sand and then wash their feather with sand. It's been known from the literature that the sand bath is crazy in generating a lot of dust. So again, we did not see that. I don't think our farm had that, but yes, you're right that if there's a certain time in the day that they're doing this, and increasing the ventilation rate just during that time is perhaps a great idea. But if I bring that to the farmers, the producers, probably they will say that it's hard in the winter because every rate of increasing the ventilation is related to further heating of the housing, and then that will be coming to the energy bill. So there will be a trade-off between their profit and then things that can do to keep the air clean. Yeah.
Excellent, Ran. Thank you. Very exciting presentation. Very useful research to the community, addressing that all the 3 case studies were extremely very important. We do have a wildfires, and probably in our context, it is been controlled. Whenever there is a wildfire happens, immediately it is been brought to the control. But I'm sure that in Canada, that the area that you mentioned was very huge.
It's huge,
sure
yeah.
It definitely will contribute significantly to the air quality. So
Yes.
just as a token of appreciation, we would like to thank from our Department of Civil Engineering, IIT Madras, and Air Quality Management Association, CEPHA network, for agreeing to give a wonderful talk in air quality management lecture series. So I also ask everyone to start your camera. We'll have one photo with Ran.
Oh, that would be great. Thank you.
All of you, please start your camera. Can all of you can start the camera? So we will take the photograph. Swaroop,
We should all thank Shivan again for organizing such lectures consistently.
I should be thankful to all the speakers, sir.
Thank you so much.
Thank you. Thank you, Ran.
Dr. Nagendra, the pleasure's on my end. Thank you very much for inviting me here. It was really exciting to see you at the conference, and then we'll keep in touch. And then I'm looking forward to interact more with you and IIT Madras. Yeah.
So, Ran, I'm just quickly to look at it. In the December we have a air quality management conference. I'm going to write to you maybe within this week or maybe in a coming week. So I'll invite you and your students can participate in that. Okay.
That would be great. I'll check my schedule, and I'm always looking for opportunity to visit or interact with India. So that would be great. Thank you very much.
Thank you, Ran, and have a good night.
Yeah, you too. Thank you.
Thank you.
Bye, everybody. Thank you for attending.
Bye bye.
Thank you, Gupta ji.
Thank you. Bye bye.
Okay. Bye bye to everybody.